In closing section 3.2, we'll try a couple of problems from this section. In the first one, we have a collar at A with negligible weight that slides without friction on the vertical bar CD. We want to determine the vertical force F that will produce an angle theta equal to 30 degrees with these three different unstretched lengths for the spring. Pause the video now and resume playing when you're ready to see a solution. Our focus will be on the collar at A, and we'll be drawing a free body diagram based on this isolating surface. We'll have a force carried by the spring. We will have a reaction force between the collar and bar CD that's purely normal, or in this case horizontal, using a standard XY coordinate system. And then we also have the force F. One of the things for us to notice is that in each case, the stretched length of the spring will be the same. That will be L equals 3 feet over cosine 30. And that number turns out to be equal to 3.464 feet. That's important because depending on the condition A, B, or C, the spring may be in tension or it may be in compression. So in cases A and B, we have respectively that L0 equals 3 feet for case A, and it's equal to 2 feet for case B. In both of those cases, the spring will be stretched, it will be in tension, and that will influence how we draw our free body diagram. In case C, the unstretched length is given as 4 feet, so in this case the spring will be in compression, and it will turn out that all the forces have the opposite signs to what we indicate in parts A and B. So here we have our collar. We're cutting through the spring. We'll give this a symbol F sub s for spring force, and this angle is theta equals 30 degrees. We have for our reaction force at A between the collar and the rod just a normal force because it slides without friction, so there's no resistance to moving in the vertical direction. And I'm drawing that off to the right because that has to offset the tension from the spring force. And we have the vertical force F that we're trying to find. For case A, the spring force is K times delta. That's 20 pounds per foot times 3.464 minus 3, or 0.464 feet. And that value is equal to 9.282 pounds. In the vertical direction, we simply have spring force sine theta minus F is equal to 0. So the vertical force required is 9.282 sine of 30 pounds. And since sine 30 is just a half, this is 4.641 pounds. Part B, the spring force is 20 pounds per foot times 3.464 minus 2, so it's 1.464 feet. And that gives us 29.28 pounds. We have the same vertical equilibrium equation, so F again is that force times sine of 30. It's ends up being half that value, half the spring force value, and that's 14.64 pounds. Finally, we'll just note in part C that everything here looks the same except for the spring force is in compression, and that's going to change the sign of everything else. So I'll go ahead and draw both the normal force reversed and the vertical force reversed. Since the spring force is now in compression, I'll write it as the spring constant times the difference between the unstretched length and the stretched length. So this is 4 minus 3.464 feet. This number turns out to be equal to 0.536 feet, and the spring force is equal to 10.72 pounds in compression. Then the vertical force F is in the positive y direction. It's again going to be equal to half of this value because it's still Fs sine 30, and that number is 5.36 pounds. As a second example, we have a problem involving a fuel pump driven by a motor-powered flywheel. We're told the pump behaves as a spring with stiffness 2 newtons per millimeter that is unstretched when alpha is equal to plus or minus 60 degrees. We'd like to know the largest tensile and compressive forces spring AB experiences during one revolution of the flywheel and state the positions alpha where these occur. The largest tensile and compressive forces occur when the spring experiences its greatest extension and compression. These are going to occur when alpha is equal to 0 degrees for maximum compression and when alpha is equal to 180 degrees for maximum tension. One of the things that makes this problem a little bit difficult is we don't actually have the unstretched length of the spring. We do know something about a state where the spring is unstretched, and we can figure out the distance between B and D under those conditions. Instead of determining the difference between a stretched and unstretched length, what we will do is determine the change in length of BD between the states where alpha is 60 degrees and the spring is unstretched, and alpha is equal to either 0 or 180 degrees, and the spring is experiencing its maximum compression or tension. Pause the video now and try the problem yourself. Resume playing when you're ready to see a solution. The solution to this problem involves more geometry than anything else, and we're again going to have to go back to our law of sines in order to determine some angles and distances so we can figure out how much stretch or compression this spring experiences. So I've sketched a triangle here showing the relationship between points D, B, and C at the configuration where the fuel pump spring is unstretched. We know alpha equals 60 degrees, so we can use the law of sines to get the angles theta and phi. We could say first that 60 millimeters over the sine of alpha, and alpha is 60 degrees to the neutral position, is equal to 20 millimeters over the sine of theta. I can rearrange that to write theta is equal to the arc sine of 20 over 60, which is a third sine of 60 degrees, and that number turns out to be equal to 16.78 degrees. I can then get the angle phi as the difference between 180 and alpha plus phi. So subtracting off 60 and then 16.78, and that gives me a value of phi of 103.22 degrees. I can then find the length of this segment BD corresponding to the unstretched length of the spring. It's not the unstretched length of the spring, but it's still going to give me a reference unstretched length that will allow me to determine the largest compression and tension of the spring under the conditions that alpha equals 0 and 180 degrees. So again, using the law of sines, I would say the reference length for BD over the sine of phi is equal to, for instance, 60 millimeters over the sine of alpha, so that's the sine of 60 degrees. And if I rearrange this, I can solve for the reference length for BD, and that turns out to be equal to 67.45 millimeters. Now I'm in a position to determine the maximum compressive and tensile forces. The maximum compression occurs when alpha is 0 degrees, and there the length of BD would simply be the length of BC plus the length of CD, and that would equal 80 millimeters. My spring force is going to be equal to K times the maximum compression, and even though I don't have the stretched and unstretched length of the springs, this delta is going to be the same as the difference between this largest length of BD and the reference length that I calculated just a moment ago. That's 2 newtons per millimeter times 80 minus 67.45 millimeters, and that number is equal to 25.11 newtons. And we'll just note here that that's a compressive state. The maximum tension occurs when alpha is equal to 180 degrees. There, the length of BD is equal to the length of BC minus the length of CD, and that's equal to 40 millimeters. Again, F is equal to K delta. This time we're in tension, and that delta is the difference between the reference length and my length of BD, 2 newtons per millimeter times 67.45 minus 40 millimeters, and that number turns out to be equal to 54.89 newtons, and we'll just make a note that in that case the spring force is in tension.